Mr. Heffron here, and here's a video on centripetal motion. Here you can see a car doing a loop-the-loop. Okay, centripetal motion is circular motion. It involves constant speed with constantly changing direction. So you want to make sure that the speed doesn't change, but you're never going the same direction. You keep changing direction. An unbalanced force must consistently push or pull the object towards the center of the circle. So in this case here, you can see we have a car, and there's the static friction on the wheels is pushing the car towards the middle of the circle. And you can see the instantaneous velocity makes a tangent line to the circle, and the unbalanced force and the acceleration are both perpendicular to the circle. Okay, centripetal or centripetal is center seeking. And so that's what the force is doing, is pushing or seeking the car towards the center of the circle. And centrifugal is center fleeing. As the car is being pushed towards the center, you will feel the door on your arm and assume that you are being pushed out of the car, which is not true, but that's just your inertia being corrected by the door, and that sensation is a centrifugal force. Okay, now what happens if the speed is not constant? Then you don't really get circular motion anymore. If you start off slow and you keep turning, you will spiral, but end up going faster, you will spiral outwards. Of course, if you maintain your speed, you will just go in a nice little circle. And if you start off fast and you keep turning in a circle, but you're slowing down, you will spiral inwards. And you can check this yourself. Try running around in circles. Which way does your foot push you? It's always pushing you towards the middle. And what happens if you do start to speed up or slow down? What happens to your circle? So now we're going to derive the equation for centripetal acceleration. So as you can see, when you do a quarter turn, the displacement from where you start to where you finish is not as long as the distance of the arc or the quarter circle. So here's our initial position, here's our final position, and here's our displacement, and here's our distance. So if you take a look at the velocity triangle, so we got our velocity down, subtract our initial velocity right here, and we can find our change in velocity. If you take this triangle and flip it, you'll see that it fits nicely and proportionally to the displacement triangle. And this is to show you that these are similar triangles. They have the same proportions. Also, this is just to make it easier for you to see that the displacement is not quite the same as the distance. It's very noticeable. There's a difference on a quarter turn. So this is called the arc, and the displacement is called the chord. So we're going to derive the equation. So we're going to take a look. So once again, the velocity triangle, the change in velocity triangle, is proportional to, or a similar triangle to, the change in position or displacement. Now because the positions are equal to the length of a radius, instead of using D's, we switch to R's. And because they have the same proportions, the change in velocity divided by the instantaneous velocity at any given time is equal to the change in position divided by the radius at any given time. And if you rearrange that, you get the change in velocity is equal to the instantaneous velocity times the displacement divided by the radius. Now, also for a quarter turn, just like to show you that as the turns get smaller and smaller, the displacement becomes closer and closer to the same as the distance. So here's a right angle turn. Here's a 45-degree turn. And you can see at a 1/16 of a turn, they're almost the same. It's hard to tell the difference between these two values. And basically, as we get to a 0-degree angle, they will be the same. And in calculus class, you'd see this as a limit. So the size of your displacement is going to be equal to the size of your distance when your time interval approaches 0 or gets close to 0. So now using the definition of instantaneous acceleration, being the change in velocity per unit time for a time of almost no time at all, 0 seconds, then the two equations can be used to derive the useful equation. So here we have the instantaneous acceleration as the limit as the time interval approaches 0. And we also know that the displacement is equal to the distance once the limit approaches 0 as well. And we've already figured out that the change in velocity is equal to the instantaneous velocity times the displacement divided by the radius. So now we're going to plug these things together. So what we're going to do is replace the change in velocity with the change in velocity equation right here. So we're going to sub this in right here. So we're going to get the instantaneous velocity, change in radius or displacement, divided by the radius times the time interval. And then we can see that we already know that the instantaneous velocity is going to be the displacement divided by time, or the displacement is equal to the instantaneous velocity times time. So we're going to replace the delta r over here with this equation. And so we're going to get instantaneous velocity times instantaneous velocity times the time interval divided by the radius times the time interval. And then the two time intervals cancel out because there's one on the top, one on the bottom, one in the numerator, one in the denominator, so they cancel out. So now that the time interval has been canceled out, it doesn't matter if we have a limit, it's just gone. And we have the instantaneous velocity times the instantaneous velocity, so we get instantaneous velocity squared divided by the radius. And as you can see from the picture, the force and the acceleration is always pointing towards the center of the circle. So here's our simple, useful formula for centripetal acceleration. It's just the speed squared, because its speed doesn't change in a circle, divided by the radius. Okay, so now traditionally we say moving towards the middle of the circle is the negative centripetal direction, so the negative c hat, and moving away is the positive c hat direction. Okay, so instead of saying towards the center, you can just use negative c hat for your direction. Okay, so now let's try using this equation in a scenario. So for example, let's say someone's traveling at 54 kilometers per hour or 15 meters per second, and they do a tight turn on a radius of 30 meters, which is close to 100 feet. So that'd be like taking a turn on a city street, but taking it too quickly at a dangerous speed of 54 kilometers per hour. So what's going to happen there? So if we take the formula we had derived, and we stick our 15 meters per second in it, and square that, divided by 30 meters, we get an acceleration of 7.5 meters per second squared. If we divide that by gravity, which is 9.8, we get 0.76 g's. So this person will feel a 0.76 g turn if they do this. Now, of course, yeah, the turn is giving 0.76 g's, but you already feel 1 g from gravity pulling you down. So if we do Pythagorean theorem, the person will actually feel a total acceleration of 1.256 g's. That means a 100-pound person will feel like they weigh 125.6 pounds. A 200-pound person would feel like they weigh 251.2 pounds, and so on and so on. Now, we're just going to look at the limits again just to show you that it really does work nicely in a different way. So first of all, circumference is the perimeter of a circle, 2 pi r. But in this case, we're going to start off with a quarter turn or a 90-degree turn. And so we need 1/4 of the circumference to find our distance. So our distance is going to be 1/4 of the circumference, and it's going to be 47.1239 meters. Now to find the time it takes to traverse this, we're going to take the distance, 47.1239 meters, and divide by the 15 meters per second. So it's going to take basically pi, or 3.14159 seconds, to make this turn. So now to find the displacement, we're going to use the law of cosines, which looks like the Pythagorean theorem. So we got delta r squared equals 30 squared plus 30 squared. Subtract 2 times 30 times 30 times cos 90. Cos 90 is just a 1, so we could have gotten away with Pythagorean theorem here, but I thought when we use the other angles later, it's just useful to use the same method every time. And when you work through the math, you will get a displacement of 42.4264 meters. So you'll notice that the chord is 90% the magnitude of the arc. So it's not quite the same yet. We're at 90%. Now finding the average velocity, so not the instantaneous, but the average velocity. Average velocity is your final velocity, subtract your initial, divided by time. So we're going to take the final velocity, and the initial is 15 east, so negative 15 east is 15 west, so it's going to look like this. And our average acceleration, you can see, is going to point towards the middle. So right around here, the average acceleration is towards the center of the circle, once again. And when we use law of cosines for this one, we get a squared equals 15 squared plus 15 squared. Subtract 2 times 15 times 15. 15 times 15 is just 15 squared again, cos of 90. So what I did here is I factored the 15 squared out. And I also factored the fact that I got two 15 squareds here, and then I got a 2 in front of 15 squared there. So I got 2 times 15 squared. So that leaves the one of those right there, and then it leaves the cos 90 of the other one. And then, if I take the square root of 15 squared, I get a 15. And I square root my a squared to get an a. So now I'm left with root 2 bracket 1 minus cos 90. It's a lot of factoring, I understand. And then we also had acceleration is equal to the change in velocity divided by time. So acceleration squared would be the change in velocity squared over time squared. That's why the time is squared right here. But of course, when I square root both sides, the time is no longer squared. All right, so now this is going to give me the change in velocity divided by the time, and I get 6.7524 meters per second squared. So that's the average acceleration for the 90-degree turn. And you'll notice it's not quite the 7.5, which is the instantaneous acceleration at any given point on this curve. Well, how about a 45-degree angle? So what if we cut the angle in half? So now our circumference will be cut in half. So instead of being what it used to be, it'll be 23.5619 because we have an eighth instead of a quarter. The distance divided by time is going to cut the time in half. So instead of pi, it'll be half a pi, 1.5708 seconds. When we do the size of the displacement, or the chord, it's going to be 22.9610. And take a look at that. Just going from a 90-degree turn to a 45, we went from a 90% difference, like 90% to 97.4%. So it's getting closer and closer to being 100% or the same. And for the acceleration, following the same steps we did before, but this time instead of a 90-degree angle, we're putting in a 45. It's the only number that changed. And of course the time was cut in half as well. We get 7.3087 meters per second squared. That's getting really close now to the instantaneous value of 7.5. But hey, we've been using an average, not an instantaneous so far. All right, but we're getting closer. Now, instead of doing this again and again, you plugged in the same steps into a computer, into a spreadsheet. So all I did was, this is the circumference formula. I found how much of a turn I was interested in, like a tenth of a turn, 3/60th of a turn, and then what would the angle be, okay? And then found the time it would take, and then I used the same steps that we used before, and I made this table. So starting off at 90 degrees, what do we have? 47.124, 42.426. So that was off by 90-something percent, so it's wrong by about 11%. Here's the 45-degree angle. So it was like 97-point-something percent correct, only 2.6% off. And as you can see, as we move down to a smaller and smaller angle, the difference between the distance and the displacement becomes essentially zero by the time we hit 0.01 degrees. And you can see the acceleration started off being pretty different from 7.5. Then it went to 6.9, 7.1, 7.3, 7.4, 7.5, 7.5, 7.5. So as the limit was approaching a small time interval of 0, and we essentially get our acceleration of 7.5. Just to show you the limit really works. And then here you can see the graph of it. As we get closer and closer to 0 degrees or 0 time, we get a nice curve approaching our asymptote, our 7.5 meters per second squared. So it just goes to show you that it works this way too. All right, so in summary, centripetal motion is a circular motion where the unbalanced force pushes or pulls towards the center of the circle, constantly correcting the direction without modifying the speed. The speed remains constant while the direction is constantly changing clockwise or counterclockwise. Centripetal versus centrifugal. Okay, centripetal means center seeking, and it's in the negative c hat direction, and centrifugal means the center fleeing, which is the positive c hat direction. So away from the center, positive c hat, towards the center, negative c hat. Centripetal acceleration, using some calculus and geometry, we derived the simple equation for determining centripetal acceleration, which is AC equals v squared over r towards the center of the circle. I hope this video has been useful. Thank you.